Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the third lecture of week 11, your lecture number 35, and this is the first part of temperature measurement systems. And in this lecture, we are going to discuss about temperature sensors, what actually is temperature as a physical quantity, the types of sensors used to measure this physical quantity, and specifically among those types, we will discuss in detail about thermocouples and RTDs, resistive temperature detectors. So let's get started with our lecture. Okay, so let's start with temperature measurement, and we will be following your chapter 14 of LNS Morris and chapter 4 of Curtis D. Johnson for temperature measurement and its design problem. So this part has been taken from mechatronic systems, but this is just the definition of temperature. Temperature is the most widely monitored parameter in science and industry, but the exact definition of temperature is still elusive. The simplest definition would relate temperature to the average kinetic energy of individual molecules that comprise the system. And as the temperature increases, the molecular activity also increases, and thus the average kinetic energy increases. The Xerox Law of Thermodynamics lays the foundation for all temperature measurements. It states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. And by replacing that third body with a thermometer, we can state that the two bodies are in thermal equilibrium if both have the same temperature. The zeroth law does not enable the assignment of a numerical value to the temperature, and for that we must refer to a standard scale of temperature. Two absolute temperature scales and two relative temperature scales are defined, and the zero temperature corresponds to the theoretical state of no molecular movement of the substance in the absolute scales, while in the relative scales, the state of zero molecular movement corresponds to a non-zero temperature. We will be mostly following the Curtis D. Johnson, chapter number 4, for the design examples and the discussing the types of sensors and their working principle. And the instructional objectives of this chapter stress on the understanding required for application of measurement and instrumentation sensors. And after this chapter, you should be able to define thermal energy, the relation of temperature scales to thermal energy and temperature scale calibrations, transform a temperature reading among Kelvin, Rankine, Celsius, and Fahrenheit temperature scales. Then we should be able to design the application of RTD Thermistor and thermocouple based temperature sensors to specific problems in temperature measurement. And we will also be able to explain the operation of other types of sensors like bimetallic strip, gas thermometers, vapor pressure thermometers, solid state sensors, and so on. And then we will be able to design the system to measure temperature using the above mentioned types of temperature sensors. So following are the four temperature scales that are currently used. These two are the absolute temperature scales and these two are the relative temperature scales. And we can see here that the temperature at these scales that corresponds to the zero thermal energy is 0 in the absolute scales, while it is a non-zero value in relative scales. So that is the only major difference between these scales. The second difference lies in the quantification of the absolute value of temperature. So some certain standards, some certain known values of temperatures at for all these four scales has been mentioned. For example, the solid water, solid liquid, and liquid gas interface. So the water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius, and we all know that. And about the gold and oxygen and so on. So these are the four scales that we will be using. And most of the time in System International, we will be sticking with the degrees Celsius. So the absolute temperature scale is one that assigns a zero temperature to a material that has no thermal energy, while a relative temperature is one that assigns a non-zero value to a material to a non-zero temperature value to a material that has no thermal energy. And in case of absolute temperature scales, we have Kelvin and Rankine, and they can be interconverted to each other using this formula, that is a predefined formula. And in case of relative temperature scales, we have degrees Celsius and Fahrenheit, and they can be converted to each other using this formula, that is also a well-defined formula. And if we want to convert some absolute temperature scales to relative temperature scales, we can use these two formulae. So you don't have to remember these formulae, that will be given in your formula sheets, and you can you can search them on internet or in any book. So you don't have to memorize these two three formulae. Now coming to the relation of temperature to thermal energy, we have to consult the Boltzmann constant. And it is possible to relate the actual temperature to the actual thermal energy. And that can be done using this formula. W is the work or energy, the thermal energy of a material, and that is related to the current temperature T of that material with this factor 3/2 K, where K is the Boltzmann constant. And again, it is possible to actually further relate this temperature to the thermal velocity of the molecules inside that material, because we know that the work or the thermal energy can be represented by half mv square, where m is the mass of that material and v square is the thermal velocity square of that material, the molecules, the thermal velocity of these molecules. So the thermal velocity and the temperature can be related to each other using this equation number 6. Again, you don't have to memorize this equation. So based on the working principles of temperature sensors, we can classify them into 10 different categories. The first one is resistance change, RTDs, resistive temperature detectors. Any material whose resistance changes with the change in temperature but have a positive temperature coefficient, so when the temperature increases, the resistance increases. The second one is the thermoelectric effect, that is the junction of two metals. Third one is the sensitivity of semiconductor devices towards temperature, and they are different from the simple resistive temperature sensors, RTDs, in terms of their temperature coefficient. So the temperature coefficient was positive for RTDs and it is negative for semiconductor based temperature sensors. So their resistance decreases with increase in temperature. Radiative heat emission, that include infrared thermometers, and thermography, that include thermal cameras, they are similar. The sixth one is thermal expansion. We can have any material that expands by increasing the temperature, and that expansion can be translated into the temperature itself. So we have liquid mercury thermometers, bimetallic strips, pressure-based temperature sensors, and so on. Resonant frequency change based temperature sensors, and in this form, in this category, we have quartz oscillators whose oscillator resonant frequency changes with the changing temperature. On number 8, we have sensitivity of optical fiber devices, and in those sensors, we have a change in light intensity, dilation or delay, the angle or the phase of light, and so on. So the properties of that fiber optic material changes, and that in turn affects these parameters of light passing through that optical fiber, and that can be translated into the change in temperature. On number 9, we have color change based temperature detectors. So they are mostly chemical based, and they are used in food industry and medicine. And at the end, we have the change of state of material. So we'll discuss these 10 types one by one in detail, and we'll try to understand the working principle of each and every one, and discuss about the properties that for which application which one is suitable, which has a better response time, and which has a better range, and which has a better sensitivity, and what is the requirement of a signal conditioning circuit for certain different types. So let's start with the RTDs, or the resistive temperature detectors. The resistive temperature detectors are the simplest and most widely used temperature detectors, and they work on the basic working principle that the resistance of a metal rises with increase in temperature. We know that the resistance of a metal piece is equal to the rho L over A at a constant temperature. L is the length of the conductor and A is the cross-sectional area of that conductor, where rho is the resistivity. Now this resistivity has a fixed value for a fixed temperature, but the resistivity of metal changes at different temperatures. So if any of these three parameters change, the resistance will change. And in case of change in temperature, the length remains almost the same, the area remains almost the same, but the resistivity changes considerably. So the resistance changes, and here we have in this plot, we have the resistance versus temperature, the normalized resistance versus temperature of two metals, nickel and platinum, and we can see that as the temperature is increasing, the resistance of these two metals is increasing. And to further add to that, the resistance change versus temperature change is non-linear. We can clearly observe it here in both these cases. In certain parts, in certain ranges, it can be considered as linear with different slope. So in case of RTDs, resistive temperature detectors, this is common plot of resistance versus temperature of one of those RTDs. And we can see that it is a fairly non-linear type of relationship. But if we can see, if we observe carefully, resistance versus temperature in this region can be approximated to be linear, then in this range can be approximated to be linear, and in this range can be approximated to be linear, all with different slopes. And if we further want to have a better approximation of this relationship within this range, we can use a quadratic approximation instead of a linear approximation. A quadratic approximation is a non-linear approximation. So what we are trying to do is to mathematically relate temperature versus resistance of RTDs in general, not for a specific material. If we know the specific material properties, we know the exact relationship of rho versus T, but that would be different for all the metals, for every different kind of alloys and everything. But in general, if we talk about RTDs, we can and we should be able to develop a general formula that would be applicable to any type of resistive temperature detectors. This linear approximation means that we are approximating this portion of resistance versus temperature to be linear. But we can see here that this linear line is being deviated from the actual line, so there must be some error. In case of quadratic approximation, this would be even more close to the actual line and the error would be smaller. So what is the linear approximation? The linear approximation is expressed using this equation number 9, where the resistance, the actual resistance, the measured resistance of that RTD is related to the change in temperature through this equation. RT naught is the resistance at temperature T naught, that is the middle temperature of this range. Right now we are talking about this range, 30 to 60 degrees. T1 is the minimum temperature, T2 is the maximum temperature, and T naught is the temperature in the middle of this range. Alpha is the fractional change in resistance per degree of temperature at T naught, and that can be found by using this expression 1 over RT naught, the resistance at temperature T naught, into R2 minus R1. R2 is the resistance at temperature T2, R1 is the resistance at temperature T1 over T2 minus T1. So this is basically the slope, and this is 1 over RT naught, the inverse of the temperature in the middle of the range. And this delta T is T minus T naught. So T is your actual temperature that you want to measure, and T naught is the middle temperature. And in case of quadratic approximation, the formula becomes a bit more complex than this one, where RT, the resistance at temperature T, this resistance RT is related to the actual temperature T by using this expression. So RT naught is again the resistance at the middle temperature. Alpha 1 is the linear fractional change in resistance with temperature, and alpha 2 is the quadratic fractional change in resistance with temperature, where delta T is T minus T naught, and the rest of the equation is similar. So let's find out what all this approximation, linear and quadratic approximation for an RTD means. In this example, it is stated that the temperature was measured using a standard thermometer. So now this RTD is not being used to measure this temperature, but this temperature is being measured using some other sensor, some standard sensor. And at that these particular values of the temperature, the resistance of the RTD were measured against each temperature. So we are asked to find the linear approximation versus temperature between 60 degrees and 90 degrees Fahrenheit. At 60 degrees, the actual resistance of the RTD was 106 ohms, and at 90 degrees, the actual resistance of the RTD was 112.2 ohms. That was the measured resistance at the known temperatures. So what we have to do to use this formula, RT into RT naught into 1 plus alpha delta T, we have to find RT naught, we have to find alpha, and we have to find delta T. So let's do that. T naught is the temperature in the middle of this range. So T naught is equal to 75 degrees Fahrenheit. RT naught is equal to 110.2 ohms, and alpha will be equal to 1 over 110.2 into R2 minus R1, that is 112.2 minus 106 over T2 minus T1, that is 90 minus 60. So we have RT naught, T naught, alpha, and now we can find the relationship between resistance and the temperature. So alpha is equal to 0.001875 per degrees Fahrenheit. RT naught is 110.2. So both of them are correct. And 75 is the midpoint. So T naught, these three are the correct values. And now using the formula, RT is equal to 110.2 into 1 plus alpha into T minus T naught. So now this is your temperature T. So in this second example, we are asked that by what percentage do these predictions of linear and quadratic approximations vary from the actual values at 60 and 85 degrees Fahrenheit. We have already developed this relationship. RT is equal to 110.2 into something for as a linear approximation of this table. So let's use it, and let's put the value of temperature 60 degrees and find the value of resistance 107.1 at 60 degrees. But if we can go back, at 60 degrees, the actual resistance was 106. We can see here. But this formula gives us R60 as 107.1. So we can see here that there is some error. Similarly, at 85 degrees Fahrenheit, if we put 85 in this formula instead of 60, we find the resistance to be 112.3. And if we go back here, at 85, our actual resistance, our measured resistance was 111.7. So again, here is some error. So in case of 60 degrees, the error was about 1%, and at 85 degrees, the error was around 0.54%. So in case of linear approximation, we are getting errors of around 0.5% to 1%, and maybe even more in some other temperatures. And now let's move on to the quadratic approximation, and let's see how much error does that have. So in case of quadratic model, for example number 5, the resistance would be again RT naught into 1 plus alpha into T minus T naught minus alpha 2 into T minus T naught. So at 60 degrees, the resistance comes out to be 106 ohms. And if we can go back, the actual value at 60 degrees was 106 ohms. So it is exactly the same with no error. How is this alpha 2 calculated? We can find the formula in our textbook. There is a zero error because the endpoint was the one that was used to determine the constants. So let's try at 85 degrees Fahrenheit. So let's put 85 instead of 60 here and 85 instead of 60 here and find the value of resistance, and that comes out to be 111.8 ohms. And if we can go back, it was 111.7 ohms. So it is fairly near to the actual value with an error of just 0.09%. So this means that clearly the quadratic approximation provides a much better approximation of resistance versus temperature. So what does all this exercise mean for you in your signal conditioning circuits designs and your temperature measurement application? If you are using RTDs as your temperature sensing devices in your design, you are getting some value of resistance and you have to find the temperature, and you will use either of these formulae, quadratic or linear. And these formulae will be applied where? Inside your microprocessors or microcontrollers. So you will be solving for T, for this T, and this would be your subject, and R will be known. So if you have the value of R and you are trying to find the temperature that is corresponding to the your measured value of R that is coming from that RTD, you can apply this or this formula. So now if your application requires you to measure that temperature very precisely, you should go for this quadratic approximation and you should use this formula without any doubt, regardless of the requirements of processing powers. But if your application allows an error of around 1 to 2%, but you don't have enough processing power for solving a quadratic equation instead of a linear equation, you should go for the linear one. If error is allowed, solving a linear equation may consume 4 machine cycles, but solving a quadratic equation may consume 14 machine cycles or even more. So there is a trade-off. Solving this equation, the second equation, this quadratic equation, requires more processing power as compared to the linear equation. So it depends on your application which one of these is more important, and then you can decide which approximation you want to apply in your own circuit design. So let's move on to some characteristics of RTDs. The sensitivity of RTDs is estimated and can be noted from typical values of the alpha naught, the linear fractional change in resistance with temperature. So the sensitivity of these devices is not very high. Then coming to the second characteristic of RTDs is the response time. And in general, RTDs have a response time of 0.5 to 5 seconds or more. The slowness of response is due principally to the slowness of thermal conductivity in bringing the device into thermal equilibrium with this environment. So the temperature has to physically flow from the environment to the device, and the response time is when they are in steady state. So the thermal equilibrium has been established, and to establish that thermal equilibrium, it takes some time. Then we have the construction of an RTD. So RTD is simply a length of wire whose resistance is to be monitored, and the more the length, the more the resistance and more the sensitivity based on the formula R is equal to rho L over A. So in higher the length, lower the area, greater the resistance, and greater the resistance, greater the sensitivity. So what we do is we cannot use an infinitely long straight length of metal. So we use structures like coils to increase the length but keep the size small, or we can use structures like this, some zigzag wires, and the effective length of this whole pattern is quite long, but the size remains small, and the width of these wires is very small, so the area is small, meaning a higher resistance. And then we have the effective range of RTDs, and that principally depends on the type of wire being used or the material of wire from which this pattern is made. So for a typical platinum based RTD, it may have a range of varying temperature from negative 100 degrees to positive 650 degrees Celsius, whereas an RTD constructed from nickel might have a specified range of minus 180 to 300 degrees. Beyond these ranges, the specified ranges for these specific materials, the material properties will change, and they cannot bear more temperature or less temperature than the specified range. And finally, we have the signal conditioning for these RTDs. So as they have their resistance changing due to the change in temperature, so any circuit that converts that resistance into a change in voltage can be used. But because the change in resistance is very, very small with the change in temperature, usually a bridge circuit is used because a bridge can detect very, very small changes of resistors, and it has a very high sensitivity as compared to your simple potential divider circuit as we discussed earlier in our class. So this may be your signal conditioning circuit. And one more thing to note here is these compensation lines, because as the change in resistance of this RTD is very small, and it is also dependent upon the change in the resistance of metal, and these wires are also based on metal, so they can contribute to a considerable error if we do not use compensation lines for this purpose. And finally, the one of the very important parameters that have to be considered while designing the signal conditioning circuits for RTDs, or in fact using RTDs for temperature sensing, is the dissipation constant. Because RTDs are a resistance, there is a power I square R dissipated by the device itself, and that power dissipation causes the device to self-heat. Slightly self-heat, but it should self-heat. And that self-heating may also cause an error in your temperature reading. And it can also upset your delicate environmental conditions. For example, your environment was very, very delicate, and it had to be maintained at a certain temperature with an accuracy of 0.01 degrees Celsius, and if the temperature rises above or below that, your operation will be affected. So the heating of your temperature sensor may add heat to your environment, and it may disturb the temperature of that environment. It may act as a heater for that environment. So we have to consider this self-heating effect due to the power dissipation across that RTD. So the first thing that comes to mind is to keep this power dissipation as low as possible. This I has to be kept as small as possible to avoid self-heating or to reduce self-heating. And typically, in case of RTD based sensors, a dissipation constant is provided in the data sheets or the specifications. So the self-heating temperature rise can be found from the power dissipated by the RTD using this dissipation constant and PD, where delta T is the rise in temperature because of self-heating, the change in temperature. P is the power dissipated in the RTD, that is I square R. This is I square R, and this is the dissipation constants, and this is the change or rise in temperature, like maybe 2 degrees or 1 degree and so on. So let's see what is the effect of self-heating through an example. So an RTD has an alpha of 0.005 per degree centigrade, a resistance of 500 ohms, and a dissipation constant of PD is equal to 30 milliwatt per degree centigrade at 20 degrees centigrade. So all these values R, PD, and alpha are at 20 degrees centigrade. This means that your T naught is equal to 20 degrees Celsius and your R T naught is equal to 500 ohms. The RTD is used in bridge circuit with R1 is equal to R2 is equal to 500 ohms, the circuit we just saw, and R3 is a variable resistor used to null the bridge. If the supply voltage is 10 volts and RTD is placed in a bath at 0 degrees Celsius, so this is your T. Find the value of R3 to null the bridge. So we had the formula RT is equal to RT naught into 1 plus alpha into T minus T naught. So let's start with this formula. Let's find out the value of R at temperature T, where T is 0 degrees Celsius. So RT naught is 500, 1 plus alpha is 0.005, T is 0 and T naught is 20. So R comes out to be 450 ohms. And if R is 450 ohms, this is your circuit. This is 500, this is 500, that is known. This is a variable resistor and this is your RTD, and at 0 degrees Celsius its resistance was calculated at 450 ohms. So one would say that to balance this bridge, this R should also be 450 ohms if we do not consider the effect of self-heating and power dissipation. But let's consider what happens if there is self-heating and some power dissipation. And for that, we have to see how much power is dissipated, and P is equal to I square R is used. We have the value of R, that is 450 ohms. So from where we can get the I? From here, because this is a 10 volt supply. So the current passing through this resistor would be I is equal to V over 500 plus 450. 10 over 500 plus 450, and that is equal to 0.011 amperes. So this means that the dissipated power is equal to 0.54 watts. And now using the formula, del T is equal to P over PD. We already know the dissipation constant. Now we know the power, so we can know how much the temperature rose because of this self-heating. So that del T comes out to be 1.8 degrees Celsius. Thus, the RTD is not actually at the bath temperature of 0 degrees, but due to self-heating, it is now at 1.8 degrees. So this means that the resistance of this RTD that we found here, this 450 ohms, was incorrect because we put the temperature of 0 degrees as T, but in fact 0 degrees was the temperature of environment, was due to self-heating. The RTD was at 1.8 degrees Celsius. So let's find out the value of R again, and that is found by putting 1.8 instead of 0 here, and that comes out to be 454 ohms. So the bridge will be nulled at 454 ohms instead of 450 ohms. So if we ignore that, our bridge will never be nulled, and this would be considered as error in our readings that we are taking from this RTD. So we should reduce this current as much as we can. Let's just see what happens if this power supply was not 10 but this power supply was 5. So this current would have been half, and that would have been 0.011 over 2, and the square of that into 450 is 1.36 into 10 raised to power 2. So the power dissipation would come out to be 0.0136 watts instead of 0.54 watts. And what would that mean for the rise in temperature? 0.030, that would result in a temperature change of 0.45 degrees, not 1.8 degrees. And that would result in the resistance change of, let me find out, 0.45 minus 20 into 0.005 plus 1 into 500, and that would become 451 ohms instead of 450 ohms. So the error is considerably reduced if we just choose a power supply of 5 volts instead of 10 volts. So we minimize the current and we reduce the error considerably. So these are the things that have to be kept in mind while using RTDs as temperature sensors and while designing the signal conditioning circuits of your RTD based temperature sensor system. So now let's move on to the next category, that is thermoelectric effect or thermocouples, that is the junction of two metals. Thermocouples are another very important type of temperature sensors that are widely used in industry, and they work on thermoelectric effects. Now, what is a thermoelectric effect? They rely on the physical principle that when any two different metals are connected together, an EMF is produced that is a function of that temperature, and that EMF is generated between the junction of those two metals. Wires of such pairs of metals are connected together at one end, and in this form they are called the thermocouples. Thermocouples are very important class of devices as they provide the most commonly used method of measuring temperature in industry. So here is temperature versus voltage output of different types of thermocouples, and this is the basic block diagram of a thermocouple where the ends of these two metal wires are joined together, and this is the equivalent circuit where the temperature at the junction produces an EMF E1 across those two open ends. So what is a thermoelectric effect and how it is produced? So when a temperature differential is maintained across a given metal, the vibration of atoms and motion of electrons is affected by that temperature. As we just saw, that temperature is directly related to the energy of those atoms and electrons. So a difference in potential, thermal potential, exists across that metal, and that potential difference is related to the fact that electrons in the hotter end of the material have more thermal energy than those that are in the cooler end, and thus they tend to drift from the hotter end towards the cooler end to maintain equilibrium. So that drift of electrons produces an electric field and an EMF. And this drift varies for different metals at the same temperature because of the differences in their thermal conductivities. For example, for copper, the thermal energy of the electrons and molecules at a certain temperature will be different from those of platinum at the same temperature. So if the circuit is closed by connecting the ends through a separate conductor using a separate material, the current flows in the closed loop. And this is the called the Seebeck effect, and this is the block diagram of that effect. Let me further clarify that. So you have a metal wire of one material, and then at this point there is temperature T1, and at this point there is temperature T2, and T1 is less than T2. So the electrons will try to drift from T2 to T1. Then you have another metal. This is metal 1 and this is metal 2. And again, it is at temperature T2 and it is at temperature T1. So the electrons will drift from T2 to T1. And when the electrons in M1 drift from T2 to T1, the drift and the magnitude of electrons, the number of electrons drifting from this end, this right end, to the left end is different as compared to this metal T2. So if we draw the equivalent circuit here, it will be like this V1 for metal 1, and it will be like this V2 for metal 2. Now let's join one end of these two metals. What's going to happen? And find your output here. So this is your detector. As the positive ends are tied together, we can simply use the KVL, and we can find out that the potential difference EAB is equal to V1 minus V2. The V1, if V1 was greater than V2, it would be a positive value, and if V1 was less than V2, it would be a negative value. And in fact, the thermocouples work for both positive and negative values of voltage output, depending upon the type of junction they are forming. And this EAB can be related to these temperatures T1 and T2, the difference in these temperatures. So this takes us to a point that we can relate T1 and T2 to this EAB, but we have to know the magnitude of both to get that EAB. Or if we want to measure one of these temperatures and we measure EAB, we have to know the second temperature to actually use the formula and convert that EAB, the measured EAB, into the second temperature, the unknown temperature. So at least one of these two temperatures has to be known and has to be fixed. And the second temperature that is being measured, that is changing, is varying, and that would become a function of your output EAB. If we close this loop, for example, this was the metal M1 and it was at T1 and T2, and if we close the loop with the same material, what would happen? This would be V1, and again this would be V1, and effectively we will get 0-volt output here. So that's why it is important to use a different metal to close the loop, and that's why it is important to form a thermocouple. That coupling with a different metal is just to have these two different voltages V1 and V2 that are produced because of that Seebeck effect when two ends of a metal are exposed to different temperatures. So this is the mathematics of Seebeck effect, explaining that how an EMF is produced. The E epsilon is the EMF produced in volts. The integral is taken from T1 to T2, that are the junction temperatures at both the ends, and the QA and QB are the thermal transport constants of these two metals. So integrate it with respect to your temperature, difference in temperature, and you will get your EMF out. And it is also known that in practice these two constants QA and QB are nearly independent of the temperature, so that an approximate linear relationship like this can be found out, where alpha is the constant in volts per Kelvin and T2 minus T1 are the junction temperatures in Kelvin. So however, this small but finite dependence of these two constants, these thermal transport constants on QA and QB, is necessary for accurate consideration. So again, if you want to have a very accurate relationship, you should use this formula. Otherwise, if some errors are acceptable, you can use this linear approximation. The characteristics of thermocouple, we just discussed that this is the junction where the temperature has to be measured, and these are the open ends, the other ends of the metal, where there is a second temperature and that temperature has to be known. So we are calling it a reference temperature. So this is our reference temperature and this is our target temperature that is to be measured. And here we have metal A and metal B connected together at one end to form a thermocouple, and at the other end they are both exposed to a same reference temperature TR, and then we have connecting leads. These connecting leads with a third material C, and they are again this C and A and C and B are forming some thermocouple at this point and at this point. So it is very important to choose this material C such that it does not have any effect of its own in the produced EMF. This C will go directly into the operational amplifier, differential amplifier. And if we want to have extension leads, it is really important to have those extension leads such that the extension lead connected with material A is made of material A, and the extension lead connected with material B is made of material B, so that this junction is a null junction and has a 0 volt output, and again this junction is a null junction having a 0 volt output, and then your reference temperature is at the end of those junction, and that is put at your at a fixed temperature, a known temperature TR T reference, and then these third metal wire T made of material C are connected to your differential op amp. Why is it important to use these extension wires? Because usually a thermocouple is used in maybe a boiler or some industrial process, and it is at a very high temperature, and usually the reference temperature is around room temperature, that is 25 degrees or 0 degrees Celsius. So it is very difficult to maintain a fixed reference temperature very near to your actual target temperature, that may be in hundreds or even near to 1000 Kelvin. So we have to run extension leads from our actual target process. For example, this is a boiler, and here is your thermocouple that is used to measure this temperature. So this is at 800 degrees Celsius, and so we have our extension leads coming from this point to our base station, and at this point we have our TR maybe at a distance of 30 meters from this actual boiler. So here it is very easy to maintain reference temperature, and then here we have our signal conditioning circuit. So how much voltage is produced at what temperature for which materials that are connected in the form of a thermocouple, that is given by thermocouple tables. So we have, let's go forward here, we have these 6 types of thermocouples based on different material combinations, the type J, T, K, E, S and R. And the ranges of these 6 types are given, that how much temperature in which range they can measure effectively. And then for this whole range, a table is given for each type. So here in appendix 3 of your textbook 1 by L.N.S. Morris, thermocouple tables are given, and these thermocouple tables are standard. You can find them on the internet, and you will find the same table everywhere for these 6 types of thermocouples. So you have the temperature in one column, and then 6 columns for these 6 types, and there are some values written in front of each temperature. So for instance, a temperature of negative 90 degrees Celsius will produce a voltage of minus 4.777 millivolts for type E, minus 4.215 millivolts for type J, minus 3.242 millivolts for type K, and so on. So this temperature is being incremented in the steps of 10 degrees Celsius. So what if you have your temperature that is negative 145 degrees Celsius? There is no value of voltage given for negative 145 degrees Celsius, or maybe minus 147 degrees Celsius for that matter. What you will do is, you will find the two values of temperature between which your desired value of temperature lies, and you find the slope, and then using that slope you can find out the value of produced EMF for the actual for that absolute actual value of temperature that you are interested in, and that method is called interpolation. So you just connect those 2 points like here, and this is one temperature, this is one temperature, this is second temperature, and here is uh, some EMF produced. So you just interpolate it, and you can find out that at this point what would be the value of EMF produced. So that is a fairly simple mathematical task. Now one more thing to note in these tables is that all of these tables have this del C, this temperature, the Tm, that is mentioned here, this Tm with respect to a Tr, and for all those tables this Tr is considered to be kept at a 0 degrees Celsius value. So what if this Tr was not 0 in your case, in your particular application? And that is a very simple case. It is just like shifting your whole curve by a fixed value. So your table was at 0 degrees reference, and this was your table. And in your case, the reference was 20 degrees. So your whole curve will be shifted by 20 degrees downward. And if in your case your reference was negative 20, your whole curve will be shifted up by 20 degrees. So that is fairly simple to calculate that. For example, so in this case, for example, here we can see that at negative 40 degrees, your type E was putting an output voltage of negative 2.254 millivolts for a reference of 0 degrees Celsius. And at 0 degrees Celsius, we will see that here all of these types have a 0 volt output because your Tr and Tm were at same temperature. So that confirms that your Tr was considered as 0 degrees for making these tables. So what if your reference was not 0 but 20 degrees in your case? So what you have to do is you have to find the value in front of the 20 degrees, the value of EMF, and that is 1.192 millivolts. And then you have to subtract this value from your actual value. You have to shift it down. So this means that if your temperature was at 0 degrees, your sensor would be it would be producing negative 2.2 millivolts for minus 40 degrees. But if your reference was at 20 degrees, your sensor would be producing negative 2.254 minus 1.192, and that comes out to be negative 3.446 millivolts instead of negative 2.254 volts. And that makes sense because previously the temperature difference was 0 and minus 40. So the difference was 40 degrees Celsius, and for 40 degrees Celsius some voltage was produced. But now the difference is 20 and minus 40, so the difference is now 60 degrees Celsius. So more voltage should be produced than this, and we can see that more voltage is being produced. And if you go up in this table, like here, the voltage output would become smaller. For instance, let's take this value of 60 degrees, 3.683 millivolts with reference to 0 degrees. But with reference to 20 degrees, that would be 3.683 minus 1.192, and that is 194 and 2. So that would be 2.491 millivolts now instead of 3.683 millivolts. And again, that makes sense because previously the temperature difference was 60 degrees Celsius, but now the temperature difference is 40 degrees. So less voltage would be produced for the same temperature, target temperature that is being measured with our reference shifted from 0 to 20 degrees. So I hope that makes sense now, and that is not very difficult to calculate. Okay, so here we have an example in which a K-type thermocouple with a 75 degrees Fahrenheit reference is producing a voltage of this much magnitude, and we are asked to find out what is the temperature of our junction that is producing this much voltage. So first we have to convert this temperature from degrees Fahrenheit to degrees Celsius, because all our tables are in degrees Celsius. So converting 75 degrees Celsius degrees Fahrenheit into degrees Celsius will give us roughly around 24 degrees Celsius. So now that is our TR. So let's see, yes, 23.9 degrees is our TR. So now note that our reference was already shifted from 0 to 24, and still that was producing a voltage of 35.56 millivolts. So let's find out in our table of type K thermocouple that to which value this 35.56 millivolts corresponds, which values of temperature, and then find out that what is the actual value of temperature that is being represented. So here are our tables, and this third column is our type K. So we'll try to search in this column 35.5 millivolts, and here we can see we have 35.3 and 35.7 millivolts for these two temperatures, 850 and 860. So if I take an average, roughly this 35 millivolts is produced by a temperature of 855 degrees Celsius with a reference of 0 degrees Celsius. Now there is a trick. Your slope was already shifted down. This 35 is now being produced by the sensor, and we are measuring it, but our reference is now at 24 degrees Celsius. So this means that our slope was already shifted down. So this 24 has to be added to this temperature, and to find out that now this 35 is being produced due to which temperature, and that would be 879 degrees Celsius. How and why? Let's find out. So here we can see 880 degrees, and we can see that 36.5 millivolts are produced if the delta T is equal to 880 degrees Celsius, right? Delta T is T minus TR, and your TR was at 0 degrees for this table. But now your TR is at 24 degrees Celsius instead of 0 degrees Celsius. And now you are producing 35.5 millivolts. And we can see here that 35.5 millivolts is produced when our delta T was 855 degrees Celsius. So for delta T to be 855 with the reference of 24, your T has to be 875. So if your T is 879 and your TR is 24, your delta T will be equal to 855, and that corresponds to 35.5 degrees Celsius. So let's see if we have calculated it correctly. And you can see here that we are getting an actual temperature of 879 degrees Celsius. That is the value we calculated. So we have to be very careful. The mistake that is usually done by the students while calculating these sorts of circuits is that we, instead of adding this, we subtract this. Actually, for the slope to shift down, we have to subtract this. But now your reference is already changed. So you have to find out what magnitude of delta T was producing this temperature. So you have to add it for calculation, because you are solving it in a reverse manner. So be very careful about that. And then coming to the characteristics of our thermocouples, the range has been defined in our table previously in this table for different types of thermocouples. This here you have the table, and in this table you have 6 types of thermocouples, and their ranges have been defined already. So let's discuss the other parameters that are associated with thermocouples, and the first one is sensitivity. And the view of the table shows that the range of thermocouple voltages is typically less than 100 millivolts. So your sensitivity for J type is 0.05 millivolt per degree centigrade, and for type S it is 0.006 millivolts per degree centigrade. That is typical. So the worst case, that is the worst parameter for these sensors, is actually their sensitivity. And why I'm saying that it is worse, because it is a very small value of voltage, and that is very prone to be corrupted by electromagnetic interference and noise signals. The range has already been discussed. The response time for these thermocouples that are being used in industry, it depends upon their relative size. So if the size is small, the response time is faster, and vice versa. So in industry, usually the response time is 10 to 20 degrees centigrade. That is the time to achieve equilibrium with your environment. But there are thermocouples that have a response time from 10 to 20 milliseconds, but they are rare. Then coming to the signal conditioning, that is the key element in the use of thermocouples, because the output voltage is very small, as we discussed earlier, and is very prone to the noise. We have to be very careful while designing the signal conditioning circuits. And in most cases, to reduce the effect of common mode noise, we use a very high gain differential amplifier with a very high common mode rejection ratio. And we know that the common mode signal is the signal that is a non-zero signal present at both ends, both inputs of the differential amplifier, and that is automatically rejected from your signal. So your actual signal is preserved. In case of thermocouples, we have to have a very accurate and fixed reference temperature for the second junction, and that reference can be achieved by multiple ways. The first one is a controlled temperature reference block. So your second node, your second junction, is placed inside a controlled temperature block, and the temperature of that junction is controlled very precisely to keep your reference temperature fixed. In another case, in the reference compensation circuits are used, and they are used in feedback, and they are the circuits that mathematically add or subtract the correction factor of your reference from your overall output. And the third, it can be done using software reference correction. So just measure the temperature at the reference junction and include it in your equation that is being solved in the software. So that equation can be implemented in hardware using a physical circuit, or that equation can be implemented in software. So that is up to you. And we'll come to both of these techniques. They are very important and interesting techniques that are being used these days. So we are going to discuss them in detail in our design problems. And then another factor that we just considered is the noise. The noise signal is always there, and our output signal of our thermocouple is not very high voltage. So the first method that is used is to use a very high gain and a very excellent CMRR differential amplifier with our thermocouple. So the common mode noise is rejected. The second one is to use a grounded stainless steel sheet at the junction, the measurement node. So what is happening here? Let me draw the circuit again. This is our one metal. This is our measurement node. This is our second junction, and here is our differential amplifier or whatever. So this is our measurement node TM. And what if we ground this node? Would there be any effect? No, there won't be. So this output voltage will still be the same that is being produced at this point and at this point. So VAB will be same, but the noise that is being added to this circuit at this junction is grounded, and the common mode noise is then rejected by this operational amplifier, this differential operational amplifier or instrumentation amplifier. So this is one way to reject the noise that is being added to this junction. And how the noise is being added to this junction? Because the thermocouple constitute an excellent antenna for pickup of noise of electromagnetic radiation, radio, TV, and other signals. So this noise is picked up by this junction itself. So that noise is right away grounded and rejected. The other noise that is being added to these wires, that is the common mode noise, and that is rejected by this operational amplifier. And then this CMRR can be very, very high, but cannot be infinity. So there will always be a common mode gain. So we have to shield these wires to reject this noise from entering these wires. And for that, we use the twisted extension wires and a grounded foil wrap to shield these wires from the external EMI. So this will shield it and it will stop it from reaching your wires and corrupting your signal through the electromagnetic interference or EMI. So these are some of the methods that are used for noise cancellation and noise compensation, and this figure is used for temperature compensation. So we have the reference temperature and we have the temperature sensor signal conditioning, and that is being added to your output so to compensate for the reference, and we'll get into the detail in the next lecture when we are designing our actual systems. So that's it for today's lecture. And in this lecture, we discussed two very, very important types of temperature sensors, RTDs, resistive temperature detectors, and thermocouples. And these two are the most widely used temperature sensors in industry. And in the next lecture, we are going to discuss the other types, quickly discuss the other types, their characteristics, their applications, and then we'll move on to actual design problems related to the top three temperature sensors, that are RTDs, thermocouples, and thermistors. We'll discuss thermistors in the next lecture. So see you in the next live session. Take good care of yourself. Till next lecture, stay safe. Allah Hafiz.